And we'll go from, let me see how the other one looks. Yeah, this is where we're going to start this time. So we'll start here. Well, I thought I had it set up. From current slide. And before I get going, just real quickly, you know about the student course evaluations? Okay, just get those done before August 8th, way before August 8th. And the other thing is about my office hours. And I think I've told you all this before, and you probably realize it. They're stated on the locator card, syllabus, and everywhere else that I have office hours on Tuesdays and Thursdays. Mondays, Wednesdays haven't changed. 8 to 8:30 in the morning and 5:30 to 6 in the evening. Okay, that's all I've got on Monday, Wednesday. But on Tuesday, Thursday, I have 8 to 8:30 in the morning also. But I have listed 10:45 until 4:30 when I usually leave to come over here. That hasn't happened in several Tuesdays and Thursdays, mostly because I've had to do things on the Birmingham campus. Today was another one of those, and Tuesday's going to be another one. In fact, the only time I'm going to be on campus Tuesday after my 8 to 8:30 time, I'll be there from 10:45 until no later than 1 o'clock because I've got a hearing at 1:30 on the Birmingham campus there. So when that hearing's over, then I'll be coming over here. So I should be available here. I'm guessing sometime after 2:30 or something like that. If I have to make many changes to our stuff, then it may be a little later than that, but I should be here for a while then. Okay, so, but then going back to Thursday of next week, I should go back to my regular time. I'll be over there from 10:45 until, I'm going to say 4:45, because I like getting over here a little sooner than right at, I'm sorry, not 4:15, leaving campus. I've been saying 4:30. I need to leave there by 4:15 to make sure if there's trains or any other problems, I'll get here in time. Okay, now, another little thing to do with that, student asked me this morning in class, and I checked it on the website, and it's really bizarre. They have it listed that final exams are Tuesday, Wednesday, and Thursday. There's no reason to have final exams both on Tuesday and Thursday because those classes only meet those days, so there's no breakdown. The Monday, Wednesday classes are all on Wednesday. So what we'll do, we'll have class on Tuesday, and I'll either give you the exam the Thursday before, or I'll make it a very short exam so you can get it into me by Thursday. Okay, so we'll just play that by ear. But we got class Tuesday and Thursday of next week, and then Tuesday of the following week. All right, that said, any questions on anything we've covered so far? Okay, my glasses are so filthy I can't see through them. Sweat and handling with my sticky fingers. Okay. Before we move on, just a little bit about the ear. And you've probably seen this in biology class, so I'm not really sure why they have it in the physics book, except it's just such a nice picture. But you will be dealing with sonography, which has to do with not the ear, but sound. And this is just how our body handles the sound. Of course, out here we have the outer ear. This is our external ear, and this part up here is called the auricle. I had forgotten that. And then that down there is the earlobe, but that's just a common name. And then you have the ear canal, the external auditory canal. That's where the sound goes in. Now notice along here you have bone here and here, and probably some fluids it looks like and other things here. So that's mostly fleshy tissue. This is pretty much bone here, okay? Then you have what they call the middle ear. Now, the outer ear or external ear and the middle ear, the borderline is the tympanic membrane, which we often call the eardrum, okay? That's what receives those tiny little vibrations of my voice that make it through the air to you, or any other sound you're hearing, that vibrates on here. Now, the vibrations here move into the middle ear. And in the middle ear, we have three main pieces here, I guess, four maybe. The malleus, which is the first part to receive that, the incus, which those vibrate together, and then the stapes in oval window, which is a rather strange name, and then a round window. Okay, now I'm not going into all this, and this is a completely different issue, but that's where the sound gets, at first, the vibrations from the tympanic membrane, they're basically amplified in the middle ear. Okay, then you get to the inner ear. Okay, and we won't go into all this, but the first part there you see is the vestibule, the semicircular canals, the cranial nerves that carry the signal from the vibrations to the brain, and the brain processes them into figuring out what you said. Here is the cochlea, which is another place where the sound gets pretty much amplified. Okay? Now, I can't say for certain, because I don't know this for sure, but somewhere in here, I believe it's in the vestibule and the cochlea, you have these little tiny filaments that receive those vibrations, and they move, and that's what gets picked up by the, and by the way, up there is then the semicircular canals. Down here was the round window, and up there is semicircular canals. And those cilia, those little fine hairs, which tend to either break off, stiffen, or something with old age, and that's why people like me tend to get so they don't hear so well. But anyway, in young people, those are very active, and that sends a signal to the brain, and it figures out what's going on. Now, I mentioned last time, I think, about perfect pitch. I don't know if you've ever had this happen. Have you ever listened to yourself on a tape recording? Does it sound like you?
Sometimes.
Sometimes, but sometimes not. We had a real good friend, and one Christmas, they came out to visit, he and his wife. They were good friends with my mom and dad, and especially my uncle. I think my uncle may have already died by then, but if not, probably all of them were together. And Andy thought it would be fun to bring out a tape recorder. Either he had gotten it for Christmas or he was going to give it to them or something like that. But he brought it out and set it up under the table when everybody was sitting around talking and laughing and just having a good time. And then later he played it. And my poor old mom, she could recognize everybody's voice on there except hers, because she didn't sound at all like her to herself. She said, "Well, who is that that's talking all the time?" And they got so tickled because it was her. But she didn't recognize her own voice. She recognized everybody else's. And I know when I listen to these recordings, I don't want to listen to them because I don't think that sounds anything like me. But it does. Why is that? Because what I hear is basically my voice is down here somewhere, and it's getting transmitted to all these bones. And I'm hearing what those bone vibrations are. I'm not hearing my sound going through here. It's going directly to the bone. And my bones don't transmit like the air does. Okay? So people with perfect pitch must know exactly what they're going to sound like. Now I don't know if that's all of the story. It's probably not, but it's a whole lot of it, because they know they're hitting those notes well. I know I'm not hitting them well. They sound all right to me, but people around me, I know that I'm not hitting the notes well. Okay, so we'll put it that way. Now, the other thing that I wanted to mention here is the eustachian tube. Do you know what that is about? Okay, that goes down to the back of your throat. Okay, and what happens here? Have you ever been in a plane ride? No. Have you ever driven up high in the mountains and come back down?
Well, hills.
Huh?
I did hills, not mountains.
Hills, okay. Have your ears ever popped when you did that?
Mm-hmm.
Okay, that's your eustachian tube. Because when you go up to a fairly high elevation, then the air gets a little thinner. Well, the air gets thinner, it gets less dense out here, more dense in here, and the eustachian tube is there to equalize the pressure. And people who go on plane flights, and especially if you have a cold or something like this, that your eustachian tube gets stopped up, I mean, people can have incredible headaches from the pressure not equalizing on either side of the, and I think it's actually happened that people have had their eardrums burst because of the pressure difference. So the eustachian tube are there to keep it from it. Now, in really bitty tiny babies, when they get a cold, that is already a small opening in it. If that closes up, then they can't equalize. And sometimes if you've ever been on, you haven't been on a plane flight, but with babies, they will scream bloody murder because their ears are hurting like crazy. And when they get all the ear infections, that's because probably the eustachian tube is transmitting, because there's not a very long trip for that, for the germs to get from the throat up into the ear, and they get those tremendous earaches. And so sometimes they'll have to go in and have a tube put in to equalize the pressure. I don't know if you've ever known of anyone with that, but I've heard of it many times. I haven't known anyone, but many times that people, they say they had to have, kids had to have a tube put in their ear to equalize the pressure because their eustachian tube was just too small and not equalizing pressure. Okay, enough of that. So that was the end of 16.3. Now we're beginning 16.4. Okay? So I think what I'm going to do is go back to my other slide, which I can hardly see now. So I think I'm going to have to move this a little bit. Okay. Let's go to this slide and go from current slide. And let's hit it. What we're talking about here is the Doppler effect. Let me get my pen set up. My writing is terrible. Okay. It refers to the variation in the frequency or the pitch heard when a source of sound and the ear are moving relative to each other. Now, the classic example of this is a train coming at a high rate of speed down the track, and they do their whistle or whatever. And that whistle, sure, it's getting closer to you, so it's getting a little louder, but also it changes its frequency. It may start out being, getting higher frequency as it gets close to you. Not that sound, but, something like that. Or when it's moving away from you, it would be, now part of that is getting softer, but the other part is going down in frequency, down in pitch. The reason is the Doppler effect, and that's what we're talking about here. And it's named after Christian Johann Doppler. He was a physicist and mathematician born in Austria, and is best known for these researches he did with this. Now, here's why that's happening. The book gives the formula first and then explains, so I'll go on and do the same thing. It seems like to me the picture would be better, but let me go on and do it. Here's F prime. Now F is frequency, and the prime is the Doppler shifted frequency. It's not the actual frequency, but it's the shift that you hear, either going up in frequency or down in frequency. Okay? Now, that's equal to F. Now, that F is the actual source frequency. Okay? That whistle on the train is not changing its sound. The whistle is the same whistle when it started, when it's coming toward you, when it's leaving, it's the same whistle. It has a fixed frequency. That's the actual frequency. But what you hear is the Doppler shifted frequency. Okay? We'll explain why in a minute, but here's part of the reason. So you take that actual frequency and multiply it by V. Well, now what is V? It's the speed of sound. I don't know. Okay, it's doing okay. It's actually the speed of sound divided by the V, which is also the speed of sound, plus or minus the velocity of the source. Okay? And that is speed of source. Okay? Now, it'll come back, I hope. Come back. Look at that. What is it doing? Why does it do this kind of stuff? All right. I'm going to wiggle and jiggle a little bit. It is actually acting like it's not going to come back. Let me do this. Does that have any influence on it? None. Let me do this. Did that do it? That did something. There it's back. I can't explain it. Okay. So this is the Doppler effect. So in my example before of the train, V sub s is the speed of the train. This makes no sense. Is the speed of the train. There she is. All right. See if I can reach over the bottom half of the alphabet here in good stead. The top half a little on the sparse side. All right. Yeah. There's something. My leg just touched it's the wire. My leg just touched the wire, and that's what did it. I've been thinking it's the plug. There we go. That is strange. Okay. This is the equation for the Doppler shift. Well, the Doppler shift is the apparent change of frequency when something's coming at you or is going away from you. And it sounds like the sound is shifting in frequency. You know it's shifting in loudness. That's not what we're talking about. Shifting in frequency. And you'll hear this also when a siren is coming, like a ambulance or a police car, and they've got their siren going. Now, especially if it has a steady thing. These police cars that go, you know, it's hard to tell because they're changing everything. But if it has a solid thing, like, when it's coming near you, it go, you know, go up in frequency. And when it's heading away from you, it goes down in frequency. That's the Doppler shift. F prime is what you hear, the shift in frequency. The actual siren is not changing frequency. It's F. That's the actual frequency. But what the difference is, the speed of sound is the same. Okay? We did speed of sound in the last section. But the denominator is the speed of sound plus or minus the speed of the source. The car, the ambulance, the train, whatever it is, what is its speed? Now here's how you think about it. Since this is in a denominator, when the denominator goes up, the number goes down. So when you use the plus sign here, that means the Doppler shift is going down. When you're increasing the denominator, you decrease that. That means that's when it's going away from you. When when it's coming toward you, then you make the denominator a smaller number by subtracting it. See that the V will then be subtracted, Vs from that. That makes the denominator smaller, making that frequency louder. That's when the thing is coming toward you. Okay? So that's how we use it. The plus sign in the denominator is used when the source is moving away. And the minus sign is when it's moving toward you. Now we're here. It's doing its weird thing again today. Okay, let's see if that did it. I've fiddled with the cord and it gets better. All right. All right, for me to erase this one? Okay. Let's go back to the other one. And this is what we're talking about. So here's person A, the guy over there, person B, the gal over here. The car is moving toward the guy. Now he's off the road, so he's not going to get hit, don't worry. But if that car is blowing its horn steadily, you know how sometimes some people's warning horn goes off and they can't get it to shut down. If this guy's going down the highway and his horn's going off and he can't shut it down, the gal will hear that frequency decreasing because, you see, sound is a pressure wave. The horn is producing a given frequency. But as it's moving more closer to the guy, those waves are getting pushed closer together, and the higher the shorter the wavelength, the higher the frequency. She's back over here, and it's getting a longer frequency because the wavelengths are getting, longer wavelengths, so it's a lower frequency. It sounds like to her the horn is dying down, not just in volume, but also in frequency. And that's the reason for the Doppler effect. Okay? Now, let's go back to, all right, to erase this one. Let's go back to the other slide and do example 1. All right. An automobile sounds its horn while passing an observer at 25 meters per second. Now, in our earlier equation, what was the, now, that is the velocity or speed of the vehicle, which we called what in that formula, previous equation? That's V sub s. So your V sub s here is 25.0 meters per second, right? I swear it's gone. Is that your phone? Oh, okay. I thought it was a projector. Huh?
It's these crazy people that annoying people.
Oh.
That calls random.
Yeah. I swear I don't know what's going on here. Last time, there it just wiggled it again. I have a feeling there's something in the wall that's messed up. something I can't get to. There we go. Okay. So 25.0 is the speed of the vehicle. Oh, it's not 0.0. It's just 25 meters per second. Yes. Sure. Okay. I'm going to put this on pause for a moment. For some reason, when I talked with Brianna, I put it on pause. I forgot to turn it back off pause. So poor folks at home, sorry Hallie and Brianna, you missed a whole bunch, but not a whole lot. Read the book. It's all there. Sorry about that. I had put it on pause and forgot to take it off. I just noticed that. Okay, so that's an example of simple harmonic motion. Now, let's get a few words in here. Displacement of an object is the distance from the equilibrium or rest position. Now, if that's your O here, let me get my pen set up. Okay, if that's your rest position right there, then the distance that you are from here, that would be this distance would be your displacement. I can't write. That's displacement. The amplitude is the maximum displacement from here to E or from here to C prime. Okay? That would be your amplitude. That's the maximum displacement from equilibrium. Okay? The maximum displacement from that. The period, remember we had period before? What symbol do we use for period? Capital T. Okay. The period of this simple harmonic motion is the time it takes to get from one position back to the equivalent position. Now, what do we mean by equivalent position? Okay. Here we're at position A, right? Okay. Now, when it goes up here, the shadow is going to go this way, and this way, and this way. Now, right here, it's going to have that same position. Is that equivalent? No, because here the shadow is going that way, and here the shadow is going this way. So it must be the same position going in the same direction. So it would have to get all the way back here and up here again. That would be one period. That would be the time it takes to make one complete cycle, the period, just like before. Okay? Period is the time required for one complete vibration. Remember, period is the time, that's why it's capital T, time required for one complete vibration. Just coming back to this position isn't good enough. It must also go back in the same direction. One complete vibration. Okay? And then, just as before, frequency is the number, same as before, number of vibrations per time interval. Okay? Number of vibrations in per unit time. Or the number of complete revolutions you make on the Ferris wheel per unit of time. Same deal. All right, let's see. No, they don't. They don't have any more of these figures here. Let me give you the same formulas we've had before. Frequency is equal to 1 over period. Because the period is a time for one complete vibration. The frequency is number of vibrations per unit time. They're inverse relationships with each other. Okay? A pendulum is one type of a frequency device. Y'all seen a pendulum before? Ever see one of those old clocks? It goes back and forth. That's a pendulum. And way back, Galileo discovered or found out that a pendulum, no matter where you start it, it takes about the same time for it to make one complete passage. Not exact, but awfully close. Okay? And because of that, then he developed the first clock, which had a pendulum in it, because it had that. Now, let me go to the other sheet, because probably it needs to be on that. So let me discard that and go back to the other one where I can write better. Okay. So a pendulum, let me get my pen back. There it is. A pendulum. Okay. It's an object suspended so it swings freely back and forth about a pivot. Okay? An object that swings back and forth about a pivot. Okay. All right. Here's just a simple example of one. Here's your pivot up here, and your things down here. You swing it up here, and it'll go back and forth from here to here to here to here to here to here, back and forth. That's a pendulum. From this point to that point. Bring it higher, it goes back and forth higher. But, okay. Now, 3 basic properties of the pendulum discovered by Galileo. I forgot he was mentioned here. Here's the first one. Now, these aren't all that crucial. The period is independent of the mass. Doesn't matter whether you have a little mass on there or a large mass, the period is independent. Number 2. The period is independent of the amplitude. Okay? Now, when the arc is small, okay? And what do we mean by small? Less than 10 degrees. Okay? So that I've drawn here is small. That is probably a lot less than 10. Do it up to 10, and the period is independent of that. Because you do it further, it'll move faster. Do it just a little bit, it moves more slowly. Okay? It's independent of the amplitude. Amplitude is how far from the equilibrium position it goes. Okay? The third, and this is our formula. Subject to those conditions, the period is given by t is equal to, that's period, remember, 2 pi, that's just that number pi, the square root of L over G, where L is the length of the pendulum. There's your L. And what is G? Y'all should remember that. What is G? The acceleration due to gravity. In the metric system, 9.80 times 10 to, 9.80 meters per second squared. It's not times 10 of anything. 9.80. Now that's here on the surface of the Earth. As long as you stay on the surface of the Earth, that's what it is. Meters per second squared, and acceleration. Okay? Or, if you're using the U.S. customary, 32.2 feet per second squared. Okay? Now, just to convince you things are okay with this, t is measured in seconds. It's a time thing, right? That's why they use capital T. The time for one complete period. Why is that not coming back? There it is. Drives me nuts. It may be that it doesn't matter what I do, it's just going to come back on its own. I don't know. I wonder if there's a heat thing in there. If it gets too hot, it shuts down, and I don't know. All right? So this is measured in second. 2 pi, pi is just a pure number. It has no units. But L is in length. That's the length. So that's going to be, say, in meters. And this is in meters per second squared. And then the meters cancel out. And 1 over 1 over second squared is second squared. Take the square root of it, and you've got seconds. So, yeah, that's the right unit. Now, if your length is measured in feet, then use feet per second squared. The second one there. Oops. Feet per second squared. The feet cancel out, and you have 1 over 1 over second squared, which is second squared. Take the square root of it, you got second. So that works well. So the period of the pendulum depends only on its length and the acceleration due to gravity. So if you happen to take your grandfather clock up to the moon, it may not work as well, okay? So don't take it. Leave it on Earth, okay? And there's a little thing called swing set physics, and you certainly could do that as well. Let's do example 1, and I think we'll be through with the chapter. How are we doing on time? Did I even get my, watch out. Whoa, we're almost in time too. So let's do example 1. All right, to erase this? Okay, we're going to need that formula, so hang on to it. Find the length. This is what you're looking for. Now they say in centimeters. So that means we're going to have to do some fiddling around here. Of a pendulum who has a period, what's the period symbol?
T.
Capital T is 1.50 seconds. Okay? Now, how are we going to find that length? What's our formula? T is equal to 2 pi times the square root of L divided by G, where G is the acceleration due to gravity. Okay? Now, since we're in centimeters, we're going to use G of the 9.8. But remember, G equal 9.80. That's meters per second squared. We want it in centimeters. So how are we going to change that meters to centimeters? There's an easy way, and then there's a way that's a little bit harder. That's what I am doing now. Does anyone know the easy way?
The easy way.
Second?
The easy way.
How do you do that? That's what I'm asking. Do you know how to do it?
Divide 4 pi. Instead pi?
Okay, yeah, but wait. Not quite yet. Okay? What we're doing here, I'm probably doing it different from the book. The easy way is just to move your decimal 2 places. Because centi means 100. How many cents in a dollar? 100. So move it 2 places. If that was $9.80, that would be 980 pennies, right? Okay? So move the 2 places that way, and you don't have to do a thing. That'd be 980 centimeters per second squared. That's the same as 9.80 meters per second squared. So if you do that the easy way, then, now, I'd sort of jumped the gun a little bit, but we're going to use that as our G later. But we want to solve for L. Well, L's all messed up there. I mean, it's under a radical and everything else. So let's isolate everything else, and let's first divide both sides by 2 pi to get that out of the way. Okay, so that's going to be 2 pi. So the 2 pi is out of there. It's on the other side now. Okay, but I still need to get rid of that radical sign. What does the radical sign mean? Square root, right? How do you undo a square root? Leave off the word root. What do you have?
Square.
Square it. So if you square this, and this is a little bizarre, but it's true, t squared over 4 pi squared, I squared the 2, but I just write pi squared, is equal to L over G. Okay? Now all we have to do is multiply by G. So we got L is equal to, that's what we're looking for, in centimeters, is equal to G t squared over 4 pi squared. Now we fill in our numbers. But for G, we use 980 centimeters per second squared times t squared. Well, t is 1.5, and t squared would be 2.25 seconds squared, okay, divided by 4 times pi squared. Okay, now I just left that as pi squared. Now, if you wanted to, you didn't have to do this. You could have left this as 1.5. Yeah, get out of there. 1.50 seconds squared. So if you want to do it on your calculator without trusting my memory of what 1.5 squared is do it this way. Okay, 980. Oh, before I do that, let's see what happens to the units. Second squares go out, and you're left with centimeters. That's what your length is. Oh, isn't that wonderful? Okay, so let's do the numbers. 980 times 1.50 squared, not square root, 1.50 squared, right? Divide that by 4, and divide again by pi squared. So you're going to have to find your pi key and then square it, but while you're dividing by that, and see what you get. Now, I know it's a little dark in here because it's getting darker outside and it may be hard to read the top of it, so I'll turn on one of the lights. Ooh, that one. Okay. Did you do it? 980 times 1.5 squared divided by 4, and then divide again by pi squared. What do you get as an answer? 0.559? Wait, okay, no. If you're in 980, you're already in centimeters, so you would have 55.9 centimeters. Now, if you had done it in meters and used 9.8 there, then you would have to move your decimal 2 places. You would have gotten 0.559 meters, move your decimal 2 places, you get 55.9 centimeters. Did you get it on your calculator that way? Oh, you did? Huh? You just.
My calculator.
Oh, I see. Okay.
Won't do it.
Yeah. Okay. Actually, it might, but it'll be a little more trouble. All right. If that's done, then your homework exercises here would be any of the odds 1 through 13. Now, there's a glossary there. If you find that useful, that may be good. There's the formulas there. They are very good. I would certainly hang on to them. And then your review questions give you sort of a conceptual idea of what's going on. The review problems are going to be more like what you see on the test. So I would do any of those odds 1 through 17. Now, what I was talking about before is back on page 450, very end of the chapter, and that's a picture of the Tacoma Narrows Bridge built across Puget Sound in Washington. And the sad news was the poor civil engineer who did that, he built a beautiful bridge. It was a wonderful bridge, except he didn't realize the natural frequency of that bridge was very close to the natural frequency of the wind blowing off the Pacific at a certain, speed that wasn't common, but it was not uncommon. And after the bridge was built, the wind picked up to that speed, and the bridge started moving slowly at first, but as the wind persisted and kept moving at that, it moved more and more. people driving over the bridge called it galloping Gertie because it really, they could feel it moving. And one day it went for a long period of time at that same frequency and literally tore the bridge apart. Just the force of the wind on its natural resonant frequency. Okay. That was the sad news. Okay.
You want us to do 49, 449, 1 through 17?
Only if you want to. Those are just additional problems that would be probably beneficial to you. The problems I really want you to do, because next time we're going to start in chapter 17, the ones I really want you to do are the ones I'm going to give you on your test for chapter 16. That's what I gave. Oh, and by the way, since she turned in hers, I can return your chapter 12 test to you. If I can find them. There they are. Okay? And here is the chapter, whatever this is, 16? Is that right? Yeah, chapter 16. All right. And again, the test bank is pretty sorry. And they left out some information on two of the problems. On number 8, it says a train traveling at a speed of 80 miles per hour, we just did one like this in Doppler frequency, approaches an observer at a station and sounds a whistle. But they don't give you the frequency of the whistle. So I had to go back, find what the answer was, and work it backwards to find out what the frequency of the whistle was. It's about 585 hertz. So that's that chicken scratch you see there. Then what is the frequency heard by the observer? Assume the sound frequency in air, sound velocity in air is 1090 feet per second. Okay? Then number 9, they did the same thing. In fact, they almost wrote it, but didn't. A car traveling away from you at 70 miles per hour is traveling away from you at 70 miles per hour. The car horn produces a sound at a frequency of, and then they just left it blank. Okay? So I had to work it backwards again, and that would be 5,000 hertz. 5,000. No, 5,000 hertz. The first one, number 8, is 585 hertz. That's the train whistle. Okay? And the car horn was 5,000 hertz. Okay? And frankly, I think those are unrealistic numbers, but they're the ones that work. All right. So, this technically isn't due until next Thursday, but please get started on it this weekend, so if you have any questions, you can ask me on Tuesday. Now, here's sort of the bad news, okay? We've only got 3 classes left, Tuesday, Thursday, and Tuesday. And we're just starting chapter 17. Frankly, I don't think we're going to get much past 17. We're not going to have time for 18 or 19 or whatever the next chapter is. So we're just going to do basic electricity, and we'll try to get as much done as possible in basic electricity. And if we get a little more done, then that'll be fine. But I'm figuring we'll probably just do basic electricity, and I'll give you the test. Now, what I think I'll do is give you the test next Thursday for the chapter, even though we'll still have the following Tuesday. That way you can get started on the test, and then Tuesday we'll finish the chapter, and at that point I'll say, okay, you might not be able to do these questions, so they may not be required. So only do the ones, when I give it to you next Thursday, the ones that we've covered up till that point, and then you'll have fewer to do. Now, I'll be here then the following Thursday, that'll be 2 weeks from tonight, to pick up your tests. So you can bring them in and tournament. And if you have any additional questions, we've got an hour and a half to work on them, so you can certainly do that. Okay?
On the 20, is the 29th on Friday?
I don't know right now. What's the day? Today, let me go on and shut this down. And that way I'll know what the day is.